So today we're looking at the mean and the standard deviation or variance of a continuous probability distribution. So this is the bottom of page 5 of our notes, and I'd like you to, first of all, to try and recall what our formula is for our discrete random variable. Now, we know that you might remember for the binomial with n and p, our expected value of x was equal to np, given in our formula sheet. But just for a standard one, you might remember when we did in grade 11, it's going to be the sum of all our probabilities times what x is. So it was sum of x times the probability that x equals x. Okay, so our formula for a continuous random variable is the same, except for instead of a sum, we're going to have an integral. So from negative infinity to infinity, it's x times f of x. So if our function is 0 everywhere except between that interval between a and b, then instead of going from negative infinity to infinity, we could just look at that integral between a and b of x times f of x. Now, I think let's just go find our formula sheet and just check to see what's there. I think our formula sheet, PDFs and worksheets. Oh gosh, there we are, right at the top. So, just having a look here. Statistics. So discrete random variable, the mean, is the sum of the probabilities times x. And we've got, for our continuous random variable, you can see that we've got from negative infinity to infinity, x times the probability of x. We're thinking of that as our function, probability function. We can use f of x there. They also have a formula here for our variance, but I often find that this formula is quite nasty applying that. So we're going to look at the formula that we used in grade 11 and apply that. So we'll just have a look at that in a moment. I'll just see if I can change this back to where we got to be. No, that's not the right place. So I'm just going back to our coursework. Continuous probability. There we go. Back to our video notes. All right. So that's our formula for expected value of x. For our variance, now we use this formula, and we even used this back in grade 10 when we were after standard deviation. It was the square root, so you might even remember this. It was the sum of the fx squareds. So it's always about summing our x squareds, and we're going to take away our mean squared. So this formula is exactly the same as what we've used before. But when we come to a continuous probability function, using that rule for expected value of x squared, we're going to see that we're going to have to actually calculate the expected value of x squared using our formula, which just means, and I could write that the expected value of x squared will be equal to the integral, again from a to b, but this time of x squared f of x. So just like the expected value of x is just a to b x times f of x, if it's expected value of x squared, we have to square our x and multiply it by f of x. So let's have a look at example 5. And we have to calculate the mean, the variance, and the standard deviation. Now, I must admit, you definitely need a line rule down the center. So I'll just make this a bit smaller and rule the line and fix that up for us. Move it across a bit. Alright, let's get a line drawn down the centre so we can use that space. I'll get rid of that ruler. And there we go. So let's have a look. Question 5. So, our mean. So the mean, mu, is equal to the expected value of x, which now notice it's 0 elsewhere, but between -4 and -2, so between -4 and -2, we need to calculate x, f of x. So, between -4 and -2, x times f of x is a half x plus 2. So just make sure you take care with your integral notation. So before we integrate, I'm just going to expand that out. So x times a half x is a half x squared, and x times 2 is 2x. So if we integrate a half x squared, it would be a half x cubed divided by 3, plus 2x used to be 2x squared divided by 2, or just x squared. So I think we'll write this as 1/6 of x cubed plus x squared. And from -4 to -2, let's do the substitution, put -2 in. So 1/6 of -2 cubed plus -2 squared, and we have to take away, putting -4 in there, 1/6 of -4 cubed plus -4 squared. So we've ended up with 1/6 of -8, or -8/6, plus -2 squared, which is just 4. And we're taking away, okay, so in our brackets we have 1/6 times 4 cubed, that's 64, plus -4, I think it looks like we're adding 16, 4 squared. So we've got -8/6, and we're adding, I'm just collecting my like terms, I'm adding 64/6, so that's just looking at these guys. And our other term, which is 4, and we're taking away 16, is -12. So that's going to leave us with -8 plus 64. If we take 8 away from 64, I think that leaves us with 56/6. And 6 goes into 56. Whoa, how many times does that go into there? 6 9s are 54. So 9 and 2 6 and a third. And if I get 9 and take away 12, that's going to leave me with 9 take away 12. I definitely think this kind of thing you'll be using a calculator for, and we could have just put this straight into our calculator without actually doing the calculus. But I thought it's a good bit of revision of calculus anyway. 9 minus 12, 9 take away 12. 12 take away 9 is 3. So we've got -3, and we've got to add a third to that. So I think it's -2 2/3. Okay, so that's our expected value of x, or in other words, our mean. And that's, yeah. Okay, so I think we'll probably pick up our calculator much earlier in the next one. So part B is the mean. I think I'm going to use this space all the way up here. I might just do a little bit more of my ruler. Sorry about that. Right, so part B, we want our variance. So var x, which is equal to the expected value of x squared minus the expected value of x. So we've already got the expected value of x. We worked that out before. That was negative 2 2/3. So down the bottom here. So we need to get the expected value of x squared. So this means between negative 4, I should say, and negative 2, we need x squared times f of x. So we need to multiply x squared times a half x plus 2, and then integrate. So going ahead and doing that, we've got x squared times a half x is a half x cubed, plus we have 2x squared, and we're integrating this. Oh, I haven't even integrated it, have I? So bad, Mrs. Lamb. So that's between negative 4 and negative 2. So a half x cubed plus 2x squared, and going ahead and integrating will be x4 over 4. So there's a 2 on the bottom end of 4 means we've got an 8. Plus we've got a 2x, so we have a cubed over 3. And this is between negative 4 and negative 2. Substituting in our numbers. So putting in a negative 2. Negative 2 to the power of 4 is going to be 16. Plus 2 times negative 2 cubed is negative 8. So minus 16 over 3. And if we take away, substituting negative 4 in there, negative 4 to the power of 4, oh, that's pretty nasty. I think that's 256. Oh, yuck. 256. I definitely think this is a calculator job. So maybe even back here with our calculators, we could do that. So that's going to be take away 2 times negative 64. So that's going to be plus 64, 128. Over, oh, just a sec. That's going to be a negative sign, I'm sorry. Minus 128 over 3. Because, yeah, sorry, negative 4 cubed is negative 64. 2 times negative 64 is that. Now, as I said, like, this stuff should be done with a calculator. How about we just grab a calculator and let's just stick this in there now. What have we got? Oh, didn't want to do that. So I really hate about this software. There we go, tidy that up a little bit. All right, so let's just integrate. So remember, when you want to integrate, go to Options, Calculus, Integral. Okay, so we've got, we could even just write it in as it is, x squared times a half x plus 2. And we want from negative 4. Oh, sorry, I didn't mean to execute that. To negative 2. And we've got 22 over 3. Oh, it doesn't want me to write that. 22 over 3. Or think of it as 7 1/3. So, our variance is equal to the expected value of, just writing this again, minus expected value of x squared. So that's, so we've got 7 1/3, and we're taking away negative 2 2/3 squared, and then working that out with our calculator, that comes to 2/9. Part C is standard deviation. So that's going to be the square root of our variance. So the square root of 2/9. And I think we'll just leave that as root 2 over 3. So that's pretty much all you have to do for a question like that. Now the only thing is that if it was tech-free, you'd have to work without a calculator, and you'd have to be able to integrate these things. So apart from integrating f of x, we're going to have to be able to integrate x f of x. And sometimes our functions look quite nasty. So I had made a note of this in our, I'll just rule this off here. If you had something more complex, and I'm going to have to make sure I check the questions that we do in our textbooks, my textbooks, because I think they've changed some of them in different versions of the textbook. So if you had a more complex function, let's choose something like f of x is equal to, and let's make it 7e to the negative 7x. So let's make that when x is greater than or equal to 0, but let's make this equal to 0 elsewhere. Maybe I should have written it the other way around. So the smaller part is 0, and then everything after x equals 0. So the sum of that area under the curve should be equal to 1. So our expected value of x becomes something that it's not integrating it, is not part of our course. So it'll be x times f of x, or x times 7e to the negative 7x. So maybe and that would have to be between 0 and infinity, because this is basically x is greater than or equal to 0. Now, we can't integrate 7x e to the negative 7x unless we use, what do we used to call it? You know, when we have differentiate, hence integrate, doing one of those. So it would be unlikely to. So essentially, what we would do is, using our calculator, we could get our calculator to actually work out, I suppose you call it the limit as k approaches infinity of 0 to k of 7x e to the negative 7x. And to get that to work on our calculator, what we're going to put into our calculator is the exact same expression. It's just that instead of using k, we're going to put, instead of that k value in there, we can put an x in, and our calculator copes with that. So let's have a look at that. So we want to integrate. Okay, so 7x e to the power of negative 7x. And we want to go between 0 and let's put an x there. So now I'm not sure how this works or why it works, but the good thing is it does. And that equals 1/7, which is actually our answer. I'm just going back to my calculator. I noticed there that I've got that written in fraction notation. I've just changed it then back to decimals. So we can see it's 0.14285. So that's one way to deal with it on your calculator. There is another way to deal with this on a calculator, and that's by just considering the area under a curve. So graphically, what we have, and we should be able to think about this without going straight to our calculator. Our graph of 7x e to the negative 7x, well, it's an e to the negative 7x, so it's one of those graphs that eventually, comes down here at the bottom. It's probably going to have a bit of a lumpy thing happening in it and come back down again. So they're saying that the area under the curve, so infinitely, that complete area, going forever, is going to equal 1. All right? So, actually, no, it's not. That's if it's the graph. I'm talking about the graph of e to the negative 7x. Oh, and that's not even that graph. Okay, I think I've confused myself now. Let's go back to this. The graph of 7x e to the negative 7x. If we actually graph that, and then trying to get the area under the curve, knowing that we don't know what k is, but if we put a sufficiently large number of k, now because of the type of graph it is, I'm pretty sure we get a graph that does look like what I've drawn over here. We don't have to go far. I think if I put in a k value of 10, it still works out. Let's go over and have a look to see what I've done. So we go to our menu and go to graph. And if you notice here, I've put in my graph 7x e to the negative 7x. Now, from my view window, I've definitely gone from 0, and I've just gone up to 10. We don't need to go very large for it to actually start calculating this area. And if I scroll down, you can see that my y value, I've just chosen something like 1. And you can just really play with that. But again, I know that my minimum y value is 0 because we're expecting some positive values in here. If I go ahead and draw that, I get a graph here. I've got that lumpy bit at the start, and then it gets really asymptotic and it gets really close to 0. And if I go ahead and use gsolve, I can get it to find the area under the curve. So I'll just go across with F6, and I'll go to the integral. I'm going to do a mixed one, F4, and select the lower limit. I'm going to choose 0 for my lower bound. I'm going to then for my upper bound, I'm just going to choose 10. Basically, because my graph went up to 10, I'll just see what that value comes up with. It takes a little while. You can see the little swirly things swirling around. And eventually, it should find the area. And notice this is just 10, so don't use a huge number. Now, you can't even see that, but you see the area, the green part, 0.14285. So it's exactly the same as the area we have here. So you can either do this graphically if you'd rather and just use a relatively large value of k. In this value, I've used 10. Or you can just put this straight into your run menu and just put an x value up there, and it also will calculate that value for us. Okay, so there's some questions here from exercise 11.4. I'll definitely have to talk to you about those because I don't want you to have to differentiate, hence integrate any of these questions, but always just go straight in with what the integral is. So I'll probably adjust those for you. Good luck.